In this video, I want to define a group and give some of the very basic properties that a group may have. In order to have a group, I need to start with a set G and some operation star. And this operation is going to need to satisfy three different axioms. The first, this operation needs to be associative. Second, there's an element E in my set G such that A star E is equal to E star A is equal to A for all A in G. So we need to be able to have an identity element. And for every element A in my set G, there is an element A inverse in G such that A star A inverse is equal to A inverse star A is equal to E. So I need my operation to be associative, I need it to contain an identity, and I need inverses. And we can represent these groups. We use this symbol here, G star. So we use our angle brackets, we write the set and the operation. So let's consider some very basic groups that we have. The first one is Z plus, the additive group of the integers. We know that additivity is associative. We know that it does contain an identity element, which is 0, and it does contain inverses, which for addition would be negatives. Equivalently, you could have the additive group of the rationals or the additive group of the reals. We have the multiplicative group of the non-zero rational numbers, so the star means we don't include 0. We know multiplication is associative. We have an identity element, which is 1, and we have inverses, which is 1 over A, the reciprocals. And this is why it's important to have this Q star, since 0 does not have an inverse. Equivalently, you could have the multiplicative group of the non-zero reals, or the multiplicative group of the positive rational numbers. Since 0 is not positive, all of these will have inverses, and they are also positive rational numbers. So groups occur abundantly in nature. We can see them in the structure of crystals, patterns of symmetry, lots of kinds of geometric transformations. And they are also the fundamental building block for more complex algebraic structures. So they are very important. Finite groups are especially important in scientific applications. So this just means that my set G has a finite number of elements. One of the most common finite groups are going to be the groups of integers modulo n, where n is an integer greater than 1. Let's consider the integers modulo 6. So we actually denote this by z with a little subscript of 6. So my actual elements in this group are going to be the numbers 0, 1, 2, 3, 4, and 5. So I do have 6 elements here. My operation is modulo arithmetic. You add two numbers and determine the remainder when you divide by 6. So for instance, 4 plus 5, we know that 4 plus 5 is 9. Dividing by 6 would give me a remainder of 3. So in this particular set, 4 plus 5 would be equal to 3. And in general, we can expand this to the idea of Zn. So Zn would contain the elements 1, 0, 1, 2, etc., all the way up to n minus 1. With this same type of operation, we would need to find the remainder when you divide by n. And it's pretty clear that this kind of addition is associative, since we'd add numbers exactly like we normally would, and then just find the remainder. My identity element is 0. And if I have an element A and I want to find A inverse, it would be equal to n minus A. So for instance, if I go back up to my integers modulo 6, 4 inverse would be 6 minus 4, which is 2, which does make sense since 2 plus 4 is 6, which would have a remainder of 0. With finite groups, we can also have operation tables, similar to how we did with just operations. So I'm going to go ahead and build the one for Z6. So our elements 0, 1, 2, 3, 4, and 5. Same thing here. And as a reminder, we always do row, star, column. So 0 plus 0 would be 0. This is 1, 2, 3, 4, and 5, since 0 is my identity element. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. And 1 plus 5 is 6, which has a remainder of 0. 2. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5. 2 plus 4 is 6, which will have a remainder of 0. And 2 plus 5 is 7, which has a remainder of 1. And we can absolutely continue this. I'm going to go ahead and write out the rest of this table here. And when we do this, we then have a clear idea of our set as well as the operation. Finally, we have a 5, 0, 1, 2, 3, 4. So here would be my operation table or my group table. Another special kind of group is known as Abelian groups. So in my 3 axioms, I needed my operation to be associative, I needed it to have an identity, and for inverses to exist. Abelian groups are commutative groups. They are groups that are commutative. We need A star B to be equal to B star A. This is not one of my original group axioms, so not every group needs to be commutative. But if it is, it's known as an abelian group. So far, all of the examples that I've looked at have been abelian groups. So let's try to figure out one that's not. And most people's go-to of something that is not commutative is matrix multiplication. So let's look at that. Here I have 6 matrices, and I claim these are a group under the standard matrix multiplication. We do know that matrix multiplication is associative, so I do have that to be holding true. I do know that I is my identity under matrix multiplication. I still need to show that all of these have inverses, as well as the fact that this is closed in the first place, that matrix multiplication would be an operation under these. And I'm going to demonstrate these ideas with building my operation table. Here's my operation table. The fact that all of these have inverses is going to come from the fact that there is an I in every row and every column. So every element will have an inverse. I can also see that if I try to multiply, for instance, B times C, so that means row B, column C, I get that the answer is A. On the other hand, if I try to multiply C times B, this time I'm going to use row C and column B, and I get that my answer is K. So therefore, this is an example of a group that is not abelian.